You see these massive cargo ships, right? And you just have to wonder, how on earth do they pack them so perfectly? It's not just about stacking boxes. It's a high-stakes puzzle where a few centimeters can mean the difference between huge profits and total disaster. So, really, how do they do it? How do the ship's officers load that vessel right up to its absolute legal limit, squeezing in every last ton of cargo, while knowing for sure it's going to be safe and legal once it hits the open ocean? Well, it all comes down to a really fascinating mix of physics, math, and some pretty clever tools. And believe me, this is literally a game of centimeters. If you underload by just a tiny bit, you could be leaving hundreds of tons and a small fortune just sitting on the dock. But if you overload, you're risking massive fines or, even worse, running aground. The margins are razor thin. All right, so here's how we're going to crack this puzzle together. First, we'll define the problem. Then, we'll get into why water itself is a huge changing variable. After that, we'll open up the ship officer's toolkit, solve a loading problem ourselves, decode that secret ruler on the side of the ship, and wrap up by revealing a tricky density trap that can catch even the pros. So let's officially frame our challenge here. The maximum cargo problem. The goal is simple to state but hard to achieve. Figure out the exact depth you can load a ship to in port so that when it sails out into the ocean, it rises up to its precise legal limit. Not 1 centimeter more, not 1 centimeter less. To solve this, we've got to start with the single most important factor in the whole equation, the water itself. Yeah, the water. Because, as you're about to see, the water in a river port and the water out in the open sea are two completely different beasts. This right here is the core principle. Salt water is just denser. It has more stuff in it, so it provides more buoyant force. It literally pushes up on the ship's hull harder, making it float higher. Fresh water, on the other hand, is less dense. It provides less lift, so the exact same ship will naturally sink deeper. Understanding this one idea is the key to everything else. So, how do officers turn this science into real-world action? Well, they're not just guessing, that's for sure. They use a very specific toolkit of formulas designed to master the effects of water density. The first tool in the box is called the Freshwater Allowance, or FWA. Now, for any given ship at a certain weight, this is a fixed number. It tells you exactly how many millimeters deeper that ship will sit in pure freshwater compared to pure saltwater. You can think of it as the ship's own personal density change value. And here's the math behind it. To find the FWA, you take the ship's total weight, which is called its displacement, and you divide it by 4 times its TPC. Now, TPC is a really crucial number. It stands for tons per centimeter, and it tells you exactly how many tons of cargo you need to load to make the ship sink by 1 single centimeter. It's like the ship's buoyancy rating. So this formula is basically using the ship's weight and buoyancy to predict its behavior. But here's the thing. In the real world, most ports aren't pure freshwater or pure saltwater. They're usually a brackish mix somewhere in between. And that's where the Dock Water Allowance, or DWA, becomes the most important tool of all. This is the calculation that tells you exactly how much deeper you can load the ship in the port you're in right now, because you know the denser seawater is going to lift it back up. You can think of this formula as figuring out where the dock water is on a scale between pure fresh and pure salt. If the dock is almost pure salt water, your allowance is going to be tiny. If it's almost pure fresh water, you'll get pretty much the full freshwater allowance. It's a precise, custom calculation for every single port, every single time. All right, theory time is over. Let's put this new toolkit to work and actually solve the puzzle. We're going to walk through a real-world scenario to find the absolute maximum cargo we can load. Okay, here's our situation. Our ship has a freshwater allowance of 150 millimeters. We're in a dock where the water density is 1.010, and we know our legal summer draft out at sea is exactly 8 meters. Our mission: figure out just how deep we can load it right here, right now. We'll nail it in 3 simple steps. So, we plug the numbers into our formula, run the calculation, and boom, 90 millimeters. That is our dock water allowance. Think of it as a 90 millimeter bonus. The extra depth we can safely and legally load the ship to, all thanks to this specific port's water. And now for the big finish. We take our legal sea draft of 8 meters and we add our 90 millimeter bonus. This means we can load the ship until the water is right at the 8.09 meter mark on the hull. And then it's like magic. As the ship sails out into that denser seawater, it will rise by exactly 9 centimeters to sit perfectly at its legal 8-meter limit.
But why does all this precision matter so much? Well, get this. If an officer made a mistake and only loaded to their sea draft while they were still in a river port, the ship would end up floating way too high once it reached the ocean. On a big ship, a small gap of just 13.6 centimeters is the same as leaving 408 tons of paying cargo on the dock. That's a massive and totally avoidable loss of money.
Now, all these calculations aren't just numbers on a computer screen. They correspond to a very real, very important symbol that's painted on the side of every single ship. You've probably seen it before. It's called the Plimsoll mark, and it's basically the ship's official ruler. Each line on this thing is a legal limit for a specific condition. S is for summer saltwater. F is for freshwater. And here's the really cool part. The physical distance between that S line and the F line is the ship's freshwater allowance, painted right there on the hull. The other marks are for different climate zones, letting you load deeper in calm tropical waters or making you load lighter for safety in rough winter seas.
But here's something you have to notice. Look closely. You will not see a line for DWA. And that's because there can't be one. The dock water allowance changes with every single port's unique water density. It's an invisible line that you have to calculate from scratch every single time you load. Okay, we've got the core concepts down, but now we're going to get into one final expert-level detail. This is the hidden calculation that separates the pros from the rookies and stops a very common and very critical mistake. Let's go back to our TPC number, tons per centimeter. The ship's official manuals will always give you the TPC for saltwater. But what happens if you use that saltwater number while you're loading in a freshwater river? You've just walked right into a trap. Here's how the trap works. On the left, we have the common mistake. Your saltwater TPC is 20, so you think loading 200 tons will sink the ship by exactly 10 centimeters. But that's wrong. Because the freshwater is weaker, it actually takes less weight to sink the ship by a centimeter. The true TPC in the river is only 19.51. That means those 200 tons will actually sink the ship by 10.25 centimeters. That quarter centimeter might seem tiny, right? But that's the error on a single load. Multiply that tiny error over thousands of tons of cargo, and suddenly your ship is centimeters deeper than you planned. That is exactly how ships run aground. So here's the expert rule. For calculating how much the ship sinks with each load, you have to use the TPC adjusted for the local dock water. But for that initial FWA formula, you must use the official TPC for saltwater. It's all about using the right tool for the right job. In the end, loading a cargo ship isn't just about manual labor. It's a precise science. It's a constant dance between maximizing what you can carry and respecting the absolute laws of physics. And as we've seen out on the high seas, every single millimeter tells a very important story of physics, finance, and safety.